Thank you very much. Now I would like to ask Mr. Kitade Atsuhisa to present the paper titled Clarification of Micromechanism on Brittle Fracture Initiation Condition of TMCP Steel with MA as the trigger point. Please take your time.
Thank you. Thank you, Chairman. I'm Atsuhisa Kitade, the University of Tokyo. Today, I'd like to talk about clarification of micromechanism on brittle fracture initiation condition of TMCP steel with MA as a trigger point. At the beginning, I'd like to show you the contents of my presentation, research of background, purpose of the study, elucidation of the microscopic mechanism of brittle fracture, development of a prediction FEM model of DWTT test, and conclusion. First, I'll explain research background. This is a figure of percentage of power generation in Japan. Even in Japan, since the nuclear power plant stopped due to the Great East Japan earthquake, the amount of electricity generated by natural gas has increased. At present, the two means of transportation are mainly used: continuous transportation by pipeline or ship transport by LNG tanker vessel. Globally, the ratio of transportation of natural gas by pipeline is 17%. The need to pass pipeline and the harsh environment is increasing year by year. So steel material used for pipeline need to have strong strength and toughness. Boundary becomes a barrier to crack growth. TMCP technology is aiming at improving the strength and toughness of steel by effectively utilizing temperature control during hot rolling and cooling process of steel and refining the base microstructure. However, regarding TMCP steel, the braking mechanism has not been clarified in detail. The purpose of the study is as follows. First, elucidating the microscopic mechanism of brittle fracture. Second, making a formula to obtain the critical stress necessary for DWTT model from microstructure information. Finally, developing a prediction FEM model of DWTT test used for pipeline steels. The DWTT test is a standard test to examine pipeline performance. If we can predict this test result from the microstructure, it will contribute greatly to the development of my new material of high strength and toughness. In this presentation, the formulation in the second paragraph is not posted because it didn't get enough result. Therefore, in the third paragraph, analysis was performed using the critical stress derived from the double notch test, and the validity of analysis was verified. First, I'll talk about elucidating the microscopic mechanism of brittle fracture. In order to deepen the knowledge concerning the mechanism of brittle fracture occurrence of TMCP, a double notch test was conducted. The material used in the experiment is this condition: rolling temperature 850 degrees Celsius, rolling reduction 50%. As shown in the figure A, the test piece has two notches. By 3-point bending, the fracture deriving force is generated equivalently to the two notch bottoms, and one notch surface breaks. So the other notch is preserved unloaded state just before crack occurrence. So, as shown in the figure C, fatigue cracking surface that didn't break. Last, we observed fractured surface caused by fatigue. The results are shown in the photograph. Clear river pattern that exhibit trigger point of brittle fracture is surrounded by black circle line. Next, we polished this specimen from the upper surface just before the brittle fracture trigger point C can be observed. Finally, the surface was processed by FIB focused ion beam and sufficiently flat surface is polished so as to obtain EBSD image. This figure is inverse pole figure map near the fracture trigger point acquired by EBSD. The portion of the black arrow is the brittle fracture trigger point. Compared with the other part of the base material, this grain size seems extremely large. The IQ map shows the sharpness of the orientation, and the portion where the direction cannot be read clearly is displayed in black. The MA, which is a brittle fracture trigger point, cannot clearly read the orientation because of its high carbon concentration and high dislocation density. Therefore, the position of MA of fracture trigger point could be identified. In summary, fracture has occurred from MA located at the edge of the large crystal grain. Next, GROD and KAM map are shown. The GROD map represents a bearing difference from the certain reference point orientation within one crystal grain. As a result, the amount of local plastic strain can be measured. In the vicinity of the trigger MA, there are places where the value of GROD is very high, red. On the other hand, the KAM map shows the bearing difference from the neighbor parts, and according to this, the left part of the MA not displayed in red. So, the strain doesn't accumulate abruptly near MA, but gradually accumulate from the corner of the crystal grain. In any case, the effect of pile-up of dislocation is large. From these, we show the past to future formulation. First, it's necessary to incorporate the maximum value of the effective crystal grain size into model, and the orientation gap to neighbor grain has to be focused more for establishment of the accurate fracture modeling. Next, I'll talk about developing a prediction FEM model of the DWTT test used for pipeline steels. Please show movie of prediction model of DWTT test. The fulcrum support is located on both sides. The hammer is an elastic body. The test piece is an elastoplastic body, and the upper part of the test piece is press-notched. The initial speed of the hammer is 7 mm per second. Mesh division of the vicinity of the propagation part was made sufficiently fine, as shown in figure. The flowchart of this analysis is shown in this figure. Brittle fracture is judged by local critical stress and ductile fracture by strain criterion. And when reaching the limit condition, node separation or element direction shall be performed respectively. Regarding the static stress-strain relationship, low temperature tensile test was carried out, and fitting was performed using the Swift equation. Regarding the dynamic stress-strain relationship, Cooper-Simmons equation was used for fitting, but in actual experiments, the result was scattered, so fitting is based on the value of thesis value. The critical principal stress, which is the criterion of brittle fracture is estimated originally from the microstructure. But in this chapter, the critical main stress is obtained by separately performing a double notch test for model development. For the critical strain, which is the ductile fracture criterion, the value was determined with reference to the shape of the specimen after the experiment. If the critical strain is increased, more strain will be accumulated before brittle fracture and the deformation of specimen will be greater. Using the ratio of the length of the upper or lower end portion of the test piece and the length of the central portion after the experiment, the critical strain was specified. The dissipated energy, GC, can be utilized as a fitting parameter. This graph shows the temperature transition of ductile fracture rate under the production condition of 850-75. From this graph, it's understood that almost ductile fractures occur at 0 degrees Celsius. But almost all fracture surface is brittle fracture at minus 40 degrees Celsius. In this paper, we analyzed the condition of these two temperatures and examine whether the temperature transition can be correctly expressed. The analysis result is being exhibited by the way that the brittle fracture surface is red. The ductile fracture area surface was gray and the unbroken surface was shown in blue. I'll show you the analysis result. Reducing the value of GC makes brittle fracture more likely to occur. When the value of GC was set to 52,000 joules per square meter, the temperature transition was correctly expressed. Finally, I'll present a summary of this research. By measuring the crystal orientation near the brittle fracture trigger point, it's highly likely that fracture will occur from the MA present in the large crystal grain, and that pile-up effect of dislocation works greatly. And we succeeded in developing a prediction model of the DWTT test used for pipeline, and we pipeline steel by using appropriate material composition formula. If we can formulate the fracture occurrence mechanism and output critical stress from micro information, we can predict fracture characteristic by only inputting the micro information into the DWTT prediction. This is the end of my presentation. Thank you very much for kind attention.
Thank you very much.